Japan has built a solar panel you can roll up like a poster, and it might be the thing that finally breaks China's grip on the sun, about a millimeter thick. A tenth the weight of the panel you're picturing right now, and it bends. Here's the strange part. Japan invented this back in 2009. Then for 16 years, almost nothing happened with it. Now it's suddenly one of the most important technologies in the entire country. And what changed in those 16 years isn't what you'd guess. It doesn't use silicon at all, the heavy, rigid material every rooftop panel has needed for decades. This was printed, on film, using a mineral called perovskite and a heavy dose of iodine, something Japan produces more of than almost any country on Earth. That single detail is why this panel might start a fight, because right now, China controls more than 80% of the world's solar supply chain. Japan used to lead that industry. Its share has since collapsed to under 1%. And ever since the Fukushima disaster in 2011, Japan has been forced to import around 90% of all its energy, one country, almost no fuel of its own, depending on the exact rival it's trying to break free from. So Japan didn't try to beat China at the old game. It walked away from it. As the man who invented this cell put it, the harder this is to make, the harder it'll be for China to copy. That's the bet. And it's enormous. By 2040, Japan wants these panels producing 20 gigawatts of power, the output of roughly 20 nuclear reactors, enough to light around 6 million homes. This coming off rooftops, walls, and windows that today just sit there doing nothing, and it's already leaving the lab. A 46-story tower going up in Tokyo is set to wear it across its outer walls. A domed baseball stadium in Fukuoka is planned to be wrapped in it entirely. So the obvious question is this: if it's this good, why isn't it on every roof in the world already? It isn't one reason, it's three. And the first one is hiding inside the panel itself, in the very ingredient that makes it work, so start there. With the ingredient, the thing that makes perovskite work is the crystal at its heart. And in almost every high-performance version built today, that crystal contains lead, a toxic metal. The same element we spent decades scrubbing out of paint and gasoline is now printed into the panel meant to help clean up the grid. Sealed inside a module on a wall, it's harmless. The danger comes at the end of the panel's life, when it cracks, or floods, or lands in a scrapyard. Lead can leach out, and a technology built to cover millions of roofs can't afford a disposal problem it hasn't solved. Japanese teams know it. Some are racing to build all organic cells with no lead at all, panels you can throw away safely. But those don't match the best ones yet. For now, the strongest perovskite still hides a poison in its recipe. That's the first problem. It's also the smallest. The second is time. A silicon panel lasts 20 to 25 years. You bolt it down and forget it exists. The first perovskite modules lasted about 10. Half the life on a roof nobody wants to climb twice. And there's a reason for that. The same reason this thing sat on a shelf for so long. Perovskite hates water. Early cells rotted in humid air. They'd bleed out power in months, sometimes weeks. A material that falls apart in the rain is worthless on a roof. For over a decade, that one flaw kept the most promising solar technology on Earth locked in the lab. So what finally changed? Not the crystal. Japan stopped trying to reinvent it and started learning to protect it instead. The breakthrough was the packaging. Using sealing layers a few atoms thick, researchers pushed the working life of some modules from 1,000 hours in the lab toward the same 25-year mark silicon has held for generations. The humidity problem didn't get cured. It got wrapped, finally well enough to matter. Then the factories caught up. And to see why that mattered so much, look at what silicon costs to make. To get the high-purity silicon inside a normal panel, you have to heat it past 1,000 degrees Celsius. That furnace is a big part of why those panels are so heavy, so stiff, and so expensive. Perovskite skips nearly all of it. Mitsui Chemicals worked out how to make the film by coating it like ink, instead of baking it in a vacuum, cutting the material cost to about a third of silicon, roughly 1,000 yen, under $7 per square meter. Their machines can print 1,000 square meters an hour. The process burns around 60% less energy than making silicon. And in a pilot in Fukushima, Toshiba ran these thin film panels to deliver steady power around the clock. Then came the number nobody expected. For years, perovskite was the promising underdog that couldn't quite keep up. Its theoretical ceiling sits above 30%, higher than silicon can ever reach. But the real world lagged far behind, until a flexible cell from Tokyo City University hit a record 26.5%. For the first time, it was nearly as good as the silicon it was built to replace. Another Japanese team went sideways instead of up, building a titanium-based version that still runs at over 90% of its output in dim, low light. 16 years of quiet work didn't change what perovskite is. It changed whether anyone could actually use it. That's the answer the opening promised. Nothing got invented in 2025. It just at last became real, which leaves the third problem, the one no lab can solve. Can Japan actually win? Because inventing a thing and owning it are not the same. Japan invented modern perovskite. But look at who holds the patents now. Chinese firms control about 56% of them. One company, Trina Solar, holds more perovskite patents on its own 481 than Japan's top firms combined. Japan's share of the field it started is barely a fifth. The same country that crushed Japanese solar the first time, driving its manufacturing below a single percent, is sprinting down this new road, too. And it is not behind. Here's the part that should worry Japan most. None of this is standing still. Every month spent scaling a factory is a month China spends filing more patents, cutting more cost, locking down more of the supply chain. Japan didn't just have to invent this. It has to win a race it's currently losing on paper. Against the exact rival it built this whole gamble to escape, so why bet the country on it anyway? Because Japan is out of easy roads. It buys about 90% of its energy from abroad. Its energy self-sufficiency sits at 12.6%, one of the lowest of any major economy. Nearly every drop of oil, every lump of coal, arrives on a ship from somewhere else. Renewable power has turned into a geopolitical weapon, and Japan is on the wrong end of it. The man behind these cells compared China's grip on kikumitsu to plain bullying. Perovskite offers the one thing no fuel ever has. A panel Japan can build from raw material to rooftop on its own soil. Using iodine, it pulls from the ground in greater volume than nearly anyone alive. A supply line no rival can cut, and the money has stopped being talk. In March 2025, the government and Mitsui Chemicals launched a national perovskite program. Tokyo handed Sekisui Chemical roughly $1 billion to build a plant turning out 100 megawatts of panels by 2027. The industry ministry herded 150 companies into one alliance. It guarantees a bonus on every kilowatt hour these panels generate to carry the technology through its expensive early years. And from April 2025, Tokyo began forcing solar onto most new homes, a rule expected to add tens of thousands of kilowatts of capacity a year. That 20 gigawatt goal you heard at the top now sits inside a wider plan. Renewables climbing toward 40% of the grid by 2030 and up to half the country by 2040, net zero by 2050, and the price per watt cut in half again along the way. Solar carries about a tenth of Japan's power today, up from under 2% a decade ago. This is meant to be the jump that dwarfs it, and it has already left the drawing board, in ways the tower and the stadium only hint at. Panasonic is building these cells straight into window glass, so a single pane can make electricity and still let the light pour through. Sekisui is wrapping flexible sheets around the curved walls of Tokyo's cruise terminal, that 46-story tower, and that domed stadium in Fukuoka, both going up right now. The whole point is that this goes where silicon never could, up walls, across windows, over curved and fragile roofs, onto every surface a crowded country owns but has never been able to use. The inventor's pitch was almost casual. Stop thinking of it as construction, and start thinking of it as a household appliance. No roof of your own? Hang one on the balcony. And if it spreads the way silicon once did, the payoff reaches far past Japan, potentially pushing global solar capacity past 500 gigawatts within a few years, and cutting billions of tons of carbon from the air every single year. So could this really change rooftops forever? Honestly? The technology works. The factories are rising. The money is committed. That much is settled. What isn't settled is the race, a fragile material Japan has to make tough, cheap, and clean fast, while the country that beat it last time holds more than half the world's patents and refuses to slow down. The invention is Japanese. The finish line belongs to whoever scales it first. But if Japan gets there, this stops being a story about a better panel. A roof stops being a roof. A window stops being just a window. Every surface a city already has quietly turns into a power plant, for a nation that until this moment had almost no power of its own. Here's what I keep circling back to, and I want your take below. Japan invented this in 2009, then let it gather dust for 16 years while China took the lead. If a breakthrough this big can be missed for that long, what else is sitting finished in some lab right now, waiting for the world to catch up?